Here we have the deep theorem that I mentioned already, the so-called Kolmogorov's 0-1 law. And the statement is that if we have a sequence of independent random variables, then either for any tail event, either the probability of the tail event is 1 or the tail event is 0, but nothing in between. The other claim is that any random variable which is measurable to this with respect to the tail sigma algebra must be constant with probability 1. So that's the theorem, and the crucial assumption is that we need independence there. It's not true otherwise, or it may not be true otherwise. With independence, we look at the sequence and we ask, okay, what happens to the tail sigma algebra? All the tail events are either happening with probability 1 or probability 0. So kind of tail is in that sense, there's no randomness in the tail. Yeah. That's kind of one way to say it again. In the tail, there's no randomness left. Because this is quite a special theorem, I think it pays off to study the proof a bit. So let's look. How would the proof go? We start with, let's denote, yes, let's see, what should we do? How to kind of get to grasp this? It looks actually quite difficult to kind of where to start the proof. The idea goes this way. We start by working, okay, what can we kind of gather from the assumption of independence? And about independence, so a way to kind of get into touch with independence is to look at this type of so-called cylinder event. So we study events of the form omega such that x1 omega is in some Borel set B1 up to, we look at up to xn, and that is some Borel set Bn. And for any Borel sets B1 up to Bn, we have an event here, and we look at all this type of events. So we look at the collection B1 up to Bn being Borel sets. So this is kind of a joint pre-images that we study. And when we want to look at what's in the tail, so then we define a collection Jn prime related to the tail, and that's similar from n+1 onwards. In this way. On the other hand, we would like to go to infinity, but we don't go there because infinity is something that we need to touch carefully. So we say n plus r in some Bn plus r. And this is a type of event that we study in the tail. And now we kind of index this collection by Borel sets n+1 up to Bn plus r, these being any Borel sets. And then we look at all the integers r. So that's how we kind of study this collection. And then what can we say about events of this sort? So imagine we pick, let's pick some event A in Jn, and let's pick some A prime in Jn prime. So if we pick these events and we calculate, okay, let's calculate now just what would be the probability of some event that observe that A is some event that we can determine by the first n random variables, because we are looking at pre-images of Borel sets there. So we look at something which is determined by the first n variables, and then we look at, okay, something that can be determined by the tail when we omit the first random variables, and we look at this joint event. And what can we say about this? Imagine now that we have fixed these Borel sets B1 up to Bn, and we have fixed Bn plus 1, Bn plus r. So we take some A and A prime of this form. So then if you look at this, what we are requiring is that actually it's the probability. This is the probability of looking at of the event that x1 is in B1, and we look at up to xn. Xn is in Bn because now we have fixed these sets and we look at this form of set. Then we also require and xn plus 1 is in Bn plus 1. And we go up to n plus r. So we look at finally xn plus r is in Bn plus r. Now you see I omitted these omegas, but I trust you that you can place them in the right place in these omegas. So the set of those omegas for which all of these conditions are true. Yep. And now we use the independence. So all of these x's are independent of each other. So we can write it as a product, of course. So we get the product of these. So this factorizes up to here, and then it factorizes until finally xn plus r. We ask it to belong to Bn plus r. Okay, we factorized everything now. On the other hand, we can also factorize back. So we can also kind of collect back in the sense that we say x1 in B1, and then we look at up to xn in Bn, yeah? And we look at the joint event that factorizes into this, and then we look at the other joint event from n plus 1 onwards up to xn plus r in Bn plus r. And what about this? This is the probability of A times the probability of A prime by definition. What did we do here? We concluded that for any events A in Jn and A prime in Jn prime, the probabilities factorize. Yes. What else do we know about these collections? I'm claiming you that both of these are pi systems. I hope you remember what was the definition of a pi system. It was some collection which is stable under intersection. Imagine you have one set of this form and another set of this form. You take the intersection. It's a homework for you to check that, yes, they really are pi systems, each of these. But that's not hard to do, so you can do it. These are pi systems. What do they generate? If you look, what would Jn generate? What sigma algebra would it generate? My claim is that actually Jn generates the sigma algebra generated by x1 up to xn. So I'm actually claiming that this generates the sigma algebra calligraphic xn. And what does Jn prime generate? Now we look at, okay, we have an events up to r, n plus r. So something was from n plus 1 up to n plus r. But we also looked at, we let r range from 1 to any arbitrarily high number. So with that understanding that also the r can be any number there. So it's possible to prove that this is a pi system which generates Tn. Okay, so we found two pi systems. these are not completely trivial, so that's why I should leave them to you. So they are generating pi systems, and what did we learn on Monday? We learned that if we can verify that probabilities factorize for pi systems, then they factorize to all events in the sigma algebras. So we learned, if we recall, the theorem about verifying independence. So then this condition for pi systems implied that the generated sigma algebras are independent. So actually what we concluded is that xn is independent of tn. And we recall that this means that the sigma algebra from x1 up to xn, this proof means that this is independent of the sigma algebra from xn plus 1 up to infinity. So look at this statement. We assume that all random variables x1, x2, etc. are mutually independent. So intuitively, of course, then the information from these is independent from the information of those. Very, very intuitive thing. But now we know how to do it formally and rigorously using measure theory. So this independence is here. And with our symbols, this is xn and the other one was tn. This was actually part one of the proof that we wanted to do. So this is part one. And let's try to remember what we are actually going to do. We are going to prove that something in the tail sigma algebra is kind of trivial for probabilities. Okay, let's go on, and we are soon there. What we want to do, namely, the second step is to note that let's remember, what did we know about T infinity? It was the intersection of all Tn's. Yeah, T infinity was the intersection of all of these, so that's why this belongs to Tn. This is true for every n. What does this imply? This implies that xn is actually independent also of T infinity. Why is this true? Because this is a smaller collection. So here we require that probabilities factorize for all pairs from these two sets. But any event in T infinity is also there. So that's why the probabilities factorize also for any pair, so that one event is from here and the other event is from there. So this is very easy. It's immediate. The tail sigma algebra is independent of any xn sigma algebra. That was part 2. Then there's one difficult part, or a little bit complicated part, part 3. That's maybe the hardest part of this proof. So here the claim is that also that's actually maybe the deep part. So I'm claiming that the x is independent of T infinity as well. Let me write maybe here that this is, at least that's my personal opinion, but in my opinion, this is the deep fact. It's deep because imagine this is the all information that we can collect from the random sequence. That's all information that we can collect from the random sequence where we are allowed to omit any finite number of observations. And the claim is here that what is eventually in the tail is independent of every element, every event in the sequence. That's really the hard and deep part. And how to get this? The idea is to define one more collection. Define a collection U by as the union of these xn's. Okay. The claim is that U is also a pi system. So U is a generating pi system. System for what? For X. Note that U is not a sigma algebra in general. So we have sigma algebras, we have a union of sigma algebras. U is not in general a sigma algebra. But U is a pi system. That should be easy to check. Well, it is easy. The less easy is to check that U really generates X. So we claim that U is generating X. That's a little bit complicated thing, but maybe it's well explained in the lecture notes. So for this one, I will refer to the lecture notes because let's see, we have finite amount of time and yes, you are well able to read. It's very well written. So that's kind of the technical part here. What does this tell us? Let me try to collect what I wanted to say here. How would this U help? Yes, in this way. So let's focus on this claim here. And now, how would we prove this claim? Is that let's pick some event in U. Okay. And then what do we know about A? Then A belongs to some xn, some finite integer n. And that's why okay, let's also pick some event in this deep tail sigma algebra. So we look at some mystical tail event E. Well, then we can calculate the probability that A occurs and this tail event E occurs. What can we say about this joint event? Because A belongs to xn, E belongs to t infinity, and by part 2, these were independent, xn and t infinity. So by part 2, xn and t infinity are independent, so then this factorizes PA, PE. Yeah. And this is now true for every A in this pi system, every E in this pi system. Yeah. So we again remember this result about Monday, verifying independence. We use that proposition to conclude that we have two pi systems, U and, well, this is a sigma algebra, so it is trivially a pi system. So we have two pi systems where we have things factorizing, so then the sigma algebras generated by these pi systems are independent. So this way. And now in the lecture notes, we learned, or we are able to learn that sigma U is equal to X. So this one is equal to X. What about this? The smallest sigma algebra generated by T infinity. Well, T infinity is already a sigma algebra, so that's why the smallest sigma algebra containing it is itself. So now we have X is independent of T infinity. Okay, and that's what we wanted to prove, the deep thing. X is independent of T infinity. Yeah. That's almost actually the proof of what we wanted to do. Where is the light? What does this actually mean? final phase is that let's maybe clean this so we can see kind of on the same whiteboard. We clean this part of the proof. And we also clean this part because we were able to prove this part 3. What next? Part 4 is that just to recognize that x belongs to, no, wrong way. The tail sigma algebra, we remember that it belongs to x. So this implies something strange. This implies that every event there is in x, so then and these are independent, so actually t infinity is independent of itself. Because if you pick a pair, one is there, one event there, so then that one event is there as well, and then we have a pair, one there, and then probability is factorized. So we get something, some claim of this sort. This is very strange because, hence, take for any event in the tail, or let's use E because that's where the lecture note author likes to use the letter. So let's pick any event E in this tail sigma algebra. Then what happens? The probability of E is equal, of course, to the probability of E intersection with itself. But now we have one event in T infinity and the other event in T infinity, and we have proved that these are independent. So by using independent in a very strange fashion, namely, we factorize this product. That's a very strange use of independence. I've never seen it used elsewhere with this form. So for me, this is a strange proof, or let's say kind of a magic. So this magic part, what does it tell us? It tells us that probability of E is equal to the probability of E squared. And what are the only numbers for which this could be true? The only numbers, the real numbers, for which the number of E is equal to its squared, so it should be 0 or 1. So for any event in the tail, the probability is either 0 or 1, because we had this. That's the end of the proof of the Kolmogorov 0-1 law of this part. So we have done this one here now. Part B will leave as a homework to read. So this will be homework reading. And it's a simple consequence of A. So